Hello guys, this is Mr. Huebner, and in this video we are going to be eventually doing a lab involving specific heat, utilizing concepts of thermodynamics to determine the specific heat of a metal. The unknown specific heat of a metal. Alright, but first we need to know, through notes you already know, specific heat is the amount of energy required to raise 1 gram of a substance 1 degree Celsius. And every single substance has its own unique specific heat. And in our experiment, we're going to be looking at heating a metal up and putting that metal into water. And we are then going to be heating that water up with that metal. We're transferring the heat from the metal into the water. We're doing that because we can record through a thermometer that liquid medium the temperature change. And through that temperature change we can calculate ultimately the specific heat of the unknown metal in this case, because we do know the specific heat of water is always 4.184 joules per gram degree Celsius, but it's the metal that we want to experimentally determine. And then we can compare it with a known value to figure out how far off we are. So, we're going to do an example problem, number 11, and we're going to be using, first of all, you got Q equals mc delta T. Q is energy, M is mass, C is specific heat, and delta T is change in temperature. And what we're going to be doing is we're going to be doing mc delta T of the metal is going to equal mc delta T of the water, medium in which we're taking the temperature of. So we've got Cm delta T of the metal equals Cm delta T of the water. And this is tricky. It's not necessarily simple, so I'm going to walk you through it. We've got a piece of unknown metal. It has a mass of 5.19. Is that going to be water mass or metal mass? Metal mass, 5.19 grams, all right. Is heated to 100 degrees Celsius. Okay, 100 degrees Celsius. So we'll keep that in mind. And it's dropped into 10 milliliters of water. All right, well that sounds like mass of water. I'm going to put that on this side. Well, it's not directly the mass. I know off the top of my head that the density of water is 1 gram per milliliter. So if you have 1 milliliter, you'd have 1 gram. If you have 10 milliliters, you'd have 10 grams. So there it is, 10 grams. Got that for my 10 milliliter of water. And the water is 22 degrees Celsius, and the metal's at 100. So those are the two initials, and the final temperature is actually going to be what we're ultimately looking for. Or no, it tells us what it is actually. And the final temperature for the system is going to be 23.83. And what that means is the 100 degrees Celsius hot metal is going to cool all the way down to the same temperature that the water is going to heat up to. So one temperature goes down, the other goes up, and they meet at, in this case, 23.83 degrees Celsius. So that's going to be our final temperature. All right. What is the specific heat capacity of the metal? Attempt to identify the metal using the attached data. Okay. Well, I don't know what the specific heat capacity of the metal is. That's what I'm looking for, so that's my C. Delta T we're going to get to. I know 4.184 joules per gram degree Celsius is the specific heat of water, and we have the change in temperature also. Alright, so what we have is energy in equals energy out. And our change in temperature is typically final minus initial. But when you do these Q equals Q problems, that's what it really is, energy in equals energy out, you're going to want to have basically an absolute value of the change. You can consider it. So we're starting at 22, and the water is rising to a temperature of 23.83. 23.83 minus 22, if you calculate it out, is 1.83 degrees Celsius. And then we are starting with 100 degrees Celsius for our metal. We're ending at 23.83. And when you subtract those two with a positive value, you're going to get 76.17 degrees Celsius. All right, so we're going to multiply these out. I'm going to multiply, and I'm going to divide both sides by 5.19 and 76.17. 5.19 and 76.17. This is very identical to the lab that you're going to be doing. Identical type of problem. So 4.184 times 10 times 1.83 equals, divided by 5.19 equals, divided by 76.17 equals our answer. So the unknown, or the specific heat of the unknown, is going to be 0.194 joules per gram degree Celsius. Yeah, the reason that is because 5.19 is grams, so grams is out of the running, degrees Celsius is out of the running. All we're left with is joules per gram degrees Celsius as our units. All right, so that's as simple or as difficult as it is. Next, we're going to get onto the actual experiment so we can see how we get these numbers in real life. This is Mr. Huebner, and we are going to get going with this specific heat lab. So in this lab, we are going to be taking a metal like this right here. This is copper, I know from experience because it's brown, and well, maybe it's not copper. So we're going to do an experiment to determine that. So I'll have to look up the specific heat of copper. And in the meantime, we're going to find the specific heat of this unknown metal. And it's pretty close to the specific heat of copper, then it's probably copper. How we're going to do that is first, we're going to heat this up via a certain medium called water. I'm going to boil the water, but I'm going to heat it up, and this is going to go inside that beaker while it is heating up. Here we go. We got a hot plate with a beaker of regular water. Just tap water is fine because it's not involved in the experiment. And here we go. I'm putting it in. And I have a string on it so that I don't burn my fingers when I'm trying to pull it out. I just pull the string out. So we're going to keep it there. But we need to be safe. So before this thing starts getting boiled, I want to make sure my goggles are on. So really, it's always a good idea to put your goggles on when you're in the lab area, especially when you are working with chemicals. Although this is a safer lab, we're working with water and copper. So I'm just going to keep them on just in case the boiling water bubbles over and goes into my eyeball. So, all right. So this is kind of the slow part. In the meantime, what I'm going to do is I'm going to take a coffee cup, also known as my calorimeter. And the nice thing about this is it's an insulated styrofoam. It has a lot of air pockets in between, which will prevent heat from leaving. And that's the whole goal. That's what we want. All right. Let's make that a bigger screen. All right, that's much better. Sorry about the small captions. So we're going to get some water. I was just reading the instructions, and it said about 100 milliliters of water would be a good amount of water to have. All right, so I'm going to go into my drawers, and I'm going to get a beaker so that I can measure 100 milliliters of dihydrogen monoxide. Alright, sorry about that. Here's my DI water, also known as deionized or distilled water. You know, I'm seeing a safety hazard. Can you see a safety hazard? That's right. We don't want this dangling into the hot plate. I'm going to take that off. Okay. So, directions. 100. 100 milliliters. Oh, okay, that's way more than 100. And this is not necessarily, this is the best, most precise way to measure something. What would be better? That's right, graduated cylinder. Fortunately, the students that were at this lab table didn't put their equipment back. Alright, I'm going to pause the video while I find a graduated cylinder. Here we are, graduated cylinder. Alright, here, let's move this up so I'm not hunching. Okay. Okay, that's my wife calling me. I'm staying at school past my curfew. Okay, I'm gonna have to call her back. Okay. There we go. It's about 100 milliliters of H2O, and I'm gonna put this into my calorimeter. Right there. Alright. I'm going to set this down right over here, and I'm going to put a thermometer into it. So let's show you what's going on here. Okay. Here's my hot water. It's going to get to a boil, making the copper also 100 degrees Celsius, the boiling point of water. And here's my coffee cup of water, distilled water. What I'm going to do is I am going to take my scalding hot copper. I'm going to put it right here as fast as I can. And normally there's little styrofoam cups, so I'm going to kind of put that in it to just try to prevent the heat from escaping. Now, is it going to be escaping from that top? Yeah, that's going to be a source of air. Not only is that going to be a source of air, but the coffee cup itself is not going to be 100% foolproof in retaining all the heat. So, are we going to have a significant percent air? Yeah, but hey, it's a high school lab. Alright, things to write down in your data table, and I will put this on a document camera in a little bit, is the mass of water in grams. We've got 100 grams. We actually have 100 milliliters. Why am I saying we have 100 grams? Because the density of H2O is 1 gram per milliliter. So if you got 1 milliliter, you have 1 gram. If you have 100 milliliters, you have 100 grams. So I'm going to put 100 grams. And I'm waiting for this thermometer to kind of have some time to do its magic in recording the temperature. It's looking like yeah, it's looking like 18. So the initial temperature of our water before metal is added is 18 degrees Celsius. And then we have the highest temperature of water in the cup after we put the copper in there. We have our T1 metal, degrees Celsius. Use the temperature of the boiling water. So water boils at what temperature? That's right, 100 degrees Celsius. So I'm going to write down 100 degrees Celsius for that. T1 of the metal. T2 of the metal is the highest temperature that's in this coffee cup, and that's going to be the same thing as T2 of the water. What's happening is the temperature of the metal is high, the temperature of the water is low, but when we put the metal in the water, they come together and equalize to the same final temperature. All right. We do have to get the mass of the metal. Normally you should do this first when it's dry, because what's going to happen when you have some water attached to that metal when you're massing it? Well, of course, you're going to get some of the mass of the water, which is going to skew your data, increasing your percent error. So shame on me. There's also the string that's involved. The string is not the metal, but we're going to be massing part of the string at least. That's going to add to our error. So there's a boatload of potential error in this experiment. The key to science is identifying it, and in the future creating new experiments that can maybe kind of get rid of some of those errors, systematic and potentially random. All right, I'm going to put pause. It's almost boiling, but I don't want to bore you with the details. So let me pause this, and then we will come back with a boiling, scalding, hot piece of metal. All right, guys, here we are. You can see in the video the little bubbles around the metal. So it is definitely boiling, and I'm going to be making an assumption that since it is boiling, the temperature of my water is 100 degrees Celsius. All right, you guys ready to do the transfer? I am. Now, when we do this transfer, we need to be doing it as quickly as possible and as safely as possible. The reason we want to do it quick is because what's happening as you transfer it is heat is radiating out from the copper metal. And we don't want it to radiate it out into the environment. We want it to radiate into the water in this calorimetry cup so that we can measure it with that thermometer. But again, it's part of the procedure. It's going to be error that's present. It's just how it is. But it's important for us to be aware of that. All right, so I'm going to transfer it. All right, and I'm going to watch the temperature in my thermometer. And again, there's air kind of, energy coming through, because I don't have a perfect lid on it. It's just how it is. And what I'm going to do is I'm going to watch the thermometer, and I'm going to watch that temperature rise. And when it stops rising, that's when I'm going to mark it as my final temperature. I was getting a little scared there. I was saying, oh my gosh, it's not changing. I'm going to have to redo this one. But I'm seeing it's going over the 20 mark, and I was looking at my original temperature. It's 18, so it definitely did rise. It's looking like it's getting close to 21. It is rising. So that's good. Okay, and I'm just mixing it so that the water can circulate, become uniform. It's at the 22 mark, actually 21.5. I'm going to pause the video and I'll come back to you if anything changes. Alright, nothing really changed in the last couple of minutes, which looks like it might slightly be going down now. So I got 21.5 degrees as my final temperature. 21.5. So I'm going to write that as my final temperature for T2 of metal and also T2 of water. I'm going to turn off this hot plate and I'm just going to let it cool off while I do my calculations. And I will dump the water out and wrap up the cord after it has had time to cool. All right. One last thing we need to do before we start doing our data processing is, you guessed it, get the mass of the metal. All right. So I'm going to get a paper towel. I'm going to dry it off as much as I can. I'm going to take this to the balance. Hey, look at that. Pugly Christmas sweater. All right. Let's see. All right. What is that telling us? Can we see that? 58.24. All right. 58.24, that's going to be our mass. .24 grams. All right, let me pause this, and we're going to get to the data processing part in just a moment. All right, so if you're following along with me and were a good listener, you would know that 58.24 was the mass of the metal. Again, I might not have gotten all of the moisture off of it, and the string was causing a little bit of extra mass to be in there. So that's going to be some error. My original temperature of the scalding hot boiling copper was 100 degrees Celsius, and my initial temperature of the coffee cup of water distilled was 18 degrees Celsius. Why did we do it in distilled water? Because in tap water there are minerals that could skew our data, because those minerals have different specific heats in the H2O and can absorb different amounts of energy. If we have distilled water, then our calculations that we're going to be doing in just a little bit for water would 100% apply. So it's going to be making sure that our calculations are precise as possible. All right. Our final temperature was, after we took the metal copper and put it into the coffee cup and let the temperature rise to its max amount, and or the metal to cool to its coolest amount, we found it was 21.5 degrees Celsius. All right, so now what we're going to do is our tabulated data table, which is where our calculations, our calculated answers go. We need to do a sample problem beneath it. So it says change in temperature of the metal. All right. So the change in temperature of the metal was final. Well, in this case, we wanted to have a positive value, so it's going to be 100 degrees Celsius minus our 21.5. Let me just put this in the calculator, make sure I don't make a goof. 100 minus 21.5. 78.5. All right. 78.5. And when you do a sample calculation, you just need one example. You don't need to do all of them. So I'm not going to show my work for my second one. My second one is the water in the calorimeter. It was starting at 18, but now it's 21.5. I'm noticing an error here. It should be the final temperature of the water minus the initial temperature in this case. So, sorry about that. So, it's going to be 21.5 minus 18. Let's calculate it. 21.5 minus 18 is 3.5 degrees Celsius. I don't need to write degrees Celsius, because I already did it in my heading, degrees Celsius. All right, next we've got to do the specific heat of the metal equation. So that's my Q equals Q, that's this one. What is it? MC delta T equals MC delta T. Here's a specific heat of water, 4.184. Times it by the mass of water, times it by my change in temperature of the water. This equals the unknown specific heat that we're looking for, times the mass of the metal, times the change in temperature of the metal. So now this is your opportunity to pause the video and try working this calculation out yourself. It'll only help you understand the information, how to do the calculations, and do better on the test. So let's pause right now. All right. I'm glad you took the time to pause and work on that. I'm just going to go over it so that we're making sure that we're doing this correctly. All right. So let's squeeze this down here and zoom. Nope. This way. There we go. 4.184 joules per gram degree Celsius is the specific heat of water, and our mass of water, if you look at it, was 100 grams. All right. 100 grams multiplied by our change in temperature, which was 3.5 degrees Celsius. And that equals our specific heat of metal, unknown metal, times the mass of metal, which was 58.24 grams, times our change in temperature of metal, which was 78.5. That's interesting that the metal change in temperature was 78.5 and the water was just 3.5. Think about it. Specific heat of water is 4.184. That's a very, very high specific heat. I'm assuming that the metal specific heat is going to be much, much, much lower, because a high specific heat means it takes a lot of energy to raise it 1 gram of that substance 1 degree Celsius. Low specific heat means it doesn't take much for it to drop or increase in temperature. Alright, so I'm going to divide both sides by 58.24 grams, and I'm going to divide both sides by 78.5 degrees Celsius so that I can isolate my C. Degree Celsius is gone, gram is gone, and I'm left with joules divided by gram degree Celsius, which is my unit for specific heat, which is what I do want. I'm now going to calculate this out. 4.184 times 100 times 3.5. I'm just pressing equal after each one just so my calculator definitely understands what I'm trying to say. Otherwise it can get all wonky. Equals, and then divide by 78.5. I'm getting 0.32. So my specific heat of my unknown metal is 0.32 joules per gram degree Celsius. All right. Off my memory, it doesn't sound very accurate at all. Let's see, here's my sheet of knowns. Oh, not bad actually. Man, I surprised myself. All right. 0.387 joules per gram degree Celsius. All right. Let's take a step back. This value is going to go into my table, 0.32. Technically, I need to have my units in the heading, so it should be joule per gram degree Celsius, and it's 0.32. I have my sample calculation under my tabulated data table. Another thing that would be good to have is our accepted value and our experimental value to figure out our percent error. So our accepted value is 0.387, and I'm going with copper. Technically, well, actually copper is the most logical one. Yeah, it's either be copper or zinc, but I know from experience that zinc is silvery, shiny, and lustrous, whereas copper is brownish, shiny, lustrous. And since this was brownish, it's probably copper. All right, so 0.387 is accepted value. 0.387 joules per gram degree Celsius is the accepted value. We then subtract the experimental value, and we divide it by the accepted value, and we times the whole thing by 100, and it's an absolute value, therefore positive. All right. 0.387 minus 0.32 divided by 0.387 times 100. All right, 17.3%. Now, 17.3% may sound like a lot, but in this experiment, that's actually relatively low. I know students that get 50% or even 120%. And I think some people have gotten lower than that. I was being sloppy. I didn't mask the metal first, so that could have increased my error. You got the string in there. Maybe I wasn't as quick as I could have been in transferring the metal to the coffee cup. I didn't have a cover on top of the coffee cup. I had a makeshift cover, but it still wasn't that great. And then there's just the coffee cup itself, which, you know, it's only going to hold so much heat in. So some of that heat was leaving the coffee cup. So there's so many places for error. It's really hard to get a low error. I'm happy with a 17.3%. So, and there you have it. That's how you determine experimentally the specific heat of an unknown metal. And fortunately, we have a lot of research and accepted values, so we can kind of compare our results to see how accurate they are. Fun little experiment. Hope you enjoyed it, and I'll see you next time.